All right. Hi everyone. We're gonna go ahead. I wanted to make a video going over some of these U substitution problems because I know they're a bit tricky and it's nice to have a video handy. So here I have our notes packet that's for 6.9. So this is the U substitution. So I was requested to do a couple of the problems in this packet. So I'm going to go over those, just a couple of those problems. And then after, I'm going to go over some of the U substitution problems from just this like extra practice worksheet that we've been working on in class. But I'll first go on over a couple of these and then we'll kind of go from there. So the first one I'm going to take a look at is example 3. We're going to look at A and B together. I'll go ahead and zoom in on A. So for A, we have the integral of sine of 2x dx. So when you do these U substitution problems, your first step is to figure out what you're going to set your U to be. And your U, you always set that to be your inner function, your function that's inside. Sometimes it can be a little bit difficult seeing our inside function, but what I can do is I can just put parentheses around this 2x just to really show that that is sine of 2x. So hopefully here we're then able to see that that inner function is going to be 2x. So we're going to set U to equal 2x. So U is that inside equation or inside function. Now I'm going to go ahead, next step is take the derivative of that. So I have du over dx is equal to, and then derivative of 2x is 2. Next, I'm going to go ahead and get dx by itself. It's stuck there in the denominator, so I can multiply dx to both sides to get out of that denominator. Then I have du is equal to 2 times dx. And then again, I'm trying to get dx by itself, so I can divide both sides by 2. So then I have du over 2 is equal to my dx. So once you get your dx by itself, your next step is to go ahead and rewrite that integral using u. So I'm just going to go up to this space up here. I have my integral symbol, and then it's sine of the 2x, but my 2x is u, so it's going to be sine of u. And then that dx, I'm replacing dx with what I got my dx to be. Dx is equal to du over 2. Okay. So we're not done yet, but just to clarify, we set u equal to our inside equation. We then took the derivative of u, got the dx by itself, and then rewrote our integral using u's. So what I can do here, I see this dividing by 2, this right here, and there's a rule that says if we're multiplying or dividing by any kind of just like plain numbers like 2, you can bring that number in front of my integral. So I'm going to rewrite that, and that's a dividing by 2, so I'm going to make sure I rewrite that as a 1 over 2. Just to show that divided by 2, it's the same thing as 1/2. Okay, so I now have 1/2, and then the integral of sine of u du. Okay. All right, so what I'm going to do now is I can go ahead and take the integral of sine of u du. So there's an integration rule that says that the integral of sine of u du is equal to negative cosine of u. So that's a rule, and it's just like there was all those derivative rules, there's all these integration rules. So the 1/2 I still have out in front, and then now I'm taking that integral, so I no longer have my integral symbol. Instead, I would just write the integral of sine of u du, which is negative cosine of u, with then a plus c at the end. Okay. And then my very last step is what I can do is I can kind of just rewrite this. I can just take this negative and put it out in front. So it's out in front of that 1/2. And then also I'm going to replace my u with what my u actually is, which in the very first step we said u was 2x. So replace u with 2x, have my plus c tagging along at the end, and there you go. So that is how you do this one. Usually for this problem in particular, usually scholars have the most amount of trouble in the very beginning with actually figuring out what to set u to equal. Okay. Nice. Let's go over and take a look at now part B. So we'll go ahead and take a look here. All right, so for number 3, part B, we're going to go ahead and start like we normally do with figuring out what we're going to set our u to be. Our u is always equal to that inside function. Here, these parentheses are pretty nice because it makes it pretty clear what that inside function is. So that inside function is going to be theta over 4. So u is equal to theta over 4. I just want to also remind you that this theta is your variable. So your theta is like your x. You treat it the exact same as your x, it's just literally a different letter. Instead of using x, they're using theta. So don't get too thrown off by that. Some scholars got thrown off. And what I'm going to do is I'm going to kind of just rewrite this. So I have u is equal to, instead of writing theta divided by 4, I'm just going to write 1/4. So 1/4 times theta. Because then in my next step, when I have to find that derivative, I'll have du over dx. The derivative of 1/4 times theta is just 1/4. So kind of rewriting it as 1/4 times theta, that allowed me to see that derivative a lot easier, I guess. So now what we need to do is go ahead and solve for dx. We need to get that by itself. So I would end up multiplying dx to both sides to get it out of that denominator right there. So then I have du is equal to 1/4 times dx. And then to get that dx by itself, I see it's being multiplied by 1/4. So you could then divide 1/4 to both sides. But that gets a little bit tricky. So instead of you can multiply by 4 to both sides. Because the 1/4 and the 4 cancel each other out. So then I have 4 du is equal to dx. So I got the dx by itself. So once I get that by itself, I can go ahead and rewrite that integral. So I'm just going to go up into this space over here. So now I have the integral, and I have cosecant squared. So I'll keep that as cosecant squared. And then in parentheses, I'm going to replace that with my u. And then the d theta, I'm going to replace the d theta with what I got. And I'm just realizing now, here, when I initially got my u and then did du, this should be du over d theta. And the reason why it's du over d theta, because our initial variable was theta instead of x. So you can see it's the end of the day. I'm getting tired, so I'm used to doing dx. But our variable is theta, so it's just d theta. But it all ends up being the same thing with dx. It's all the same. So sorry about that. So all those dx's should have just been d thetas. Hopefully that didn't mix up the video too much. Hopefully you're okay. D theta, because our variable is theta. Okay, cool. So now I go back to, okay, d theta, and I replace my d theta with what I got d theta to be right here. So that was 4 du. Okay. So now what I can do now, I look at my integral and I see I'm multiplying by this number of 4. So anytime you're multiplying or dividing by a number, you can bring that out in front of your integral. So I'm going to take that 4 and just rewrite it out in front of my integral. And then I have cosecant squared of u du. Now I can go ahead and integrate this, and there is a integration rule that says the integral of cosecant squared of u du, that is equal to negative cotangent of u plus c. So I still have my 4 in front, and then I integrate it and I get negative cotangent of u, and then with a plus c at the end. So now what I'm going to do is I'm just going to rewrite this. So I'm just going to put that negative in front of the 4. So now I have negative 4 cotangent. And then for that u, I'm going to plug back in what my original u was, which was theta over 4. And then I have my plus c. Okay. So that is this problem. Your inner function is the theta over 4. And then you take the derivative of that. Just be extra careful, be better than me. Just see that if you're doing a derivative of something with a theta, then it's du over d theta. If it was an x, then it's du over dx. But here it's theta, so it's du over d theta. And then you want to get that d theta by itself. Okay, cool. So now I'm going to go ahead and do a couple of the problems from, I'll do 1 or 2 problems from the extra practice integration worksheet. So let me grab a new one of those for myself and we'll put it on right now. Okay. So this packet right here has, it's on Canvas with the answer key. It has some really, really good practice problems. With these types of worksheets, these skill builder worksheets, they're set up so you work on the problem in box number 1. You get its answer and then you find it somewhere, and then wherever it is, that will be the next problem you work on. So I'll do the first 2. Okay, so we have the integral of e to the 6x dx. My advice for you, whenever you have an integral that has an e in it, always set your exponent on that e to be your u. So again, anytime you have an integral that has an e in it, set that exponent equal to u. So my u is going to be 6x. Then I'm going to go ahead and take the derivative of that. And notice it's dx, so I have du over dx is equal to derivative of 6x is just 6. I then get dx by itself. So I'm not going to go show all those steps. Essentially, you're just multiplying dx to both sides and then dividing by 6. And you end up getting dx is equal to du over 6. So now when you get that dx by itself, then you go ahead and rewrite that integral. So I have the integral of e, and then that 6x, that's our u, so e to the u. And then that dx, let's replace it with our du over 6. Okay. At this point, I can look for anything that I can take and move outside of the integral. So for example, this dividing by 6, I can go ahead and move that out front. I'm dividing by 6, that means I'm going to bring out a 1 over 6 out in front. And then I have the integral of e to the u du. There is an integration rule that says the derivative of e to the u du is just e to the u plus c. So I still have my 1 over 6 there, and then now I can take that integral, so that would be e to the u plus c. So then for my final answer, all I need to do is just replace that u with what we had our u to be. So that becomes 1 over 6 e to the 6x plus c, and that is my answer. Okay. So then now what I do is I just look for that answer somewhere in this packet. Let's see. Oh, look, it's right there. That's so cool. We're so smart. So now this is our next problem that we're going to do. So now this is problem number 2. And I'll go through this one with us, and then maybe that'll be it. Okay. So I have the integral of x times this parenthesis group that has an exponent of 6 dx. So first step is set u to be equal to your inner function. This one's pretty nice because hopefully you agree with me. It's pretty clear to see what our inner function is. Our inner function would be our x squared plus 2. So u is x squared plus 2. So now we're going to go ahead and take the derivative of that. So we have du over dx is equal to 2x. We solve for dx, we get by itself. We do a little bit of algebra and you end up getting dx is equal to du over 2x. Okay. Once you get the dx by itself, you can go ahead and rewrite that integral. So I'll just go up to this space. I have my integral. This x right after that integral symbol, we didn't do anything with it, so it just stays there. We haven't touched it, we didn't do anything, we just ignored it, so it's still there. It's still there. And then I have this parenthesis group where we set that inside of that parenthesis group to be u. So I'll replace that all with u. Close the parenthesis group. And then that parenthesis group has an exponent of 6. So I just need to put that 6 on it. Something I want to mention is I saw a lot of scholars set this problem up really well. They were feeling great, but they forgot to include that exponent of 6. So when you rewrite that integral, always double check if that u should have an exponent attached to it, like it does here. A lot of scholars forgot about that little 6 there. So then they didn't include it and then they ended up getting it wrong. So just be really careful. Don't forget about the little 6 there. Okay, and then I just need to replace my dx with what I found my dx to be. So dx was the du over the 2x. Okay. Now here I'm looking at this integral and I'm kind of panicking a little bit, and maybe you are as well, because you cannot have an integral with multiple variables. You can't have an integral with x's and u's all at the same time. It doesn't work. You have to have either only x's or only u's. So we're doing u substitution. So we want the u's, but we want those x's, they're causing problems. But it's kind of nice because those x's, we have an x up here and then an x down here. So they actually end up canceling each other out, which is great because now those x's are gone and they were the thing that was causing a problem. Now we have an integral with just u's. Also, at the same time, that dividing by 2, remember I can take that and put that in front of my integral symbol. So what I'm going to do is I'm going to take that dividing by 2, write that as 1 over 2. And then now I'm left with u to the 6 du. And that's a much nicer looking integral because I don't have x's and u's, it's just u's. So now I can actually go ahead and do that. Okay. So now what we're going to do is we're going to go ahead and find this integral using our regular integral power rule. So the 1/2 is still there. And that integral power rule just says add 1 to that exponent. So that exponent is now 7. And then divide by that new exponent, divide by 7. And then always have a plus c at the end. What I can do now in my last step is I can actually go ahead and multiply this 1/2 times the u to the 7 over 7. So I can just multiply the numerators together and then those denominators together. So I end up with getting, I'll just write over here, u to the 7 over 14 plus c. And then my very, very last step is I need to replace that u with what I had my u to be. So my, I'll just squeeze it down here. My u was the x squared plus 2. That u had an exponent of 7, so I got to squeeze in that little exponent of 7. And it's over 14 plus c. And because it's getting a little crammed, I'll put that in a box, in a red box. So there you go. So I substituted that u in, and I just wanted to be careful to see that that was u to the 7. So when I put that x squared plus 2 in, I need to make sure I include that exponent of 7. You can kind of see that it's pretty common mistake to forget about that exponent of 7. Just like how it's kind of easy to forget about that exponent of 6. Always double check to see if there should be some exponent somewhere. Okay, and then what you do is you just look for this answer somewhere, and that's what you do. Hopefully this helps. All right, so I'm going to go ahead and continue on to this next problem. This is number 3. And I originally wasn't going to do this problem. I was just going to have us just kind of end the video here. But I've had a lot of scholars ask me for this one, so I figured it might be good to go over it. So for this one, the most commonly asked question I'm asked for this one is, what do we set our u to be? And some scholars were thinking you maybe set u to be 4x. And if you did it, if you tried it and then got to the point where you rewrote your integral, you're going to see that things don't really cancel out and you'll have an integral with x's and u's, which is a problem. If you think back to the problem we just did, remember when we rewrote that integral, it was pretty nice that those x's canceled out. The problems are usually set up like that. So when you're doing a problem and things aren't canceling out and you have x's and u's, and chances are you may have picked the wrong u. So I'm going to actually suggest that you don't set u to be 4x. You could try it, but it won't work out. Instead, you actually have 2 different options. You could set u to be sine of 4x, or you could set u to be cosine of 4x. They end up both working because when you then set u to be one of those, and then you find the derivative of sine, let's say that's your u, derivative of sine is cosine. So things are going to end up canceling there. On the flip side, if you picked u to be cosine of 4x, the derivative of that u will give you a negative sign. So then those things will get canceled out. So actually, no matter what, either of those could be your u. Your answer will look no matter whatever one you pick, your answer will look slightly different, but it's still correct. It's just like different ways of expressing the same answer. So what I'm going to do is I'm just going to set u to equal the sine of 4x. Okay. So I have u is equal to sine of 4x. Again, this will still work if you set u to be cosine of 4x, but it both works. But I'm going to do sine of 4x. Okay, so then what I need to do is I need to now go ahead and take the derivative. So I'll have du over dx, and then just be really careful here because to take the derivative of sine of 4x, you have to use the chain rule there. And to be honest, I even forgot about that. So what you do, perhaps I'll throw some parentheses around the 4x. You take the derivative of this. So using the chain rule, you take the derivative of the inside function. Derivative of 4x is 4. And then next you go to the outside. Derivative of sine is cosine, and then it's cosine of the exact same inner function. So our derivative is 4 cosine of 4x. Just be careful with that. I forgot about that when I first did this one. Okay, so then now you're going to go ahead and get dx by itself, multiply it to both sides, do all that stuff, and you will end up getting dx is equal to du over 4 cosine of 4x. Okay. Now that we got that dx by itself, I can go ahead and rewrite that integral using u's. So I have the integral. That sine of 4x, we said that was our u, so I'm just going to write that as u. Cosine of 4x, I didn't do anything with that, so I'm just going to leave that as cosine of 4x. And then dx, I'm going to replace that dx with what I got down here. So dx is now du over 4 times cosine of 4x. Now, do you see some things that cancel? Yeah, well, hopefully you do, because this integral, if you don't cancel anything out, this integral would be a problem because you can't have an integral with u's and x's. So when that happens, you cross your fingers and hope that those x's cancel out, which they do, because cosine of 4x shows up there and it shows up down there. So both of those will cancel each other out, which is really nice. Also, at the same time, I have this divide by 4, so I can move that out in front. So I now have 1 over 4, and then the integral of u du. And that's a much nicer looking integral. It has only just u's. We're happy with that. So then now I can go ahead and take the integral of this, and I would just use my normal integral power rule. I'll want to remind myself that the exponent on that u is technically a 1. So when I integrate it, I still have my 1/4 out in front. And then I'll have u, and I add 1 to that exponent. So that would be u to the 2. And then I divide by that new exponent. So I divide by 2, and then plus c. Now I can kind of just clean this up. I can multiply these two fractions together. So I'll multiply the numerators together. So I get u squared over, and then I'm multiplying the denominators together. So I get 8, and then plus c. And then for my final step, I need to replace that u with what I originally had my u to be. So I would have sine of 4x, all of that squared over 8 plus c. And I'll put a red box around that so it jumps out a little bit more. So there you go. That would be my answer. And again, just to clarify, this would still work. You could still do this problem if you set u to be the cosine of 4x. If you did that, your answer would look slightly different, but it's still the same. So for example, when I look for this in my packet, I'm going to actually just show you exactly where it shows up right here. So notice there's two different answers, but that's because two different looking answers. These are actually equivalent. They're actually the same thing. They just look different. It's just all depends on what you set your u to be. So you can see we got this one down here. Okay. Hopefully that helps, my friends.